Hello, my name is Jason Zhang, and this is Lab 1 Charged Tapes for Physics 2212. Here's the table of contents, and let's get started with the purpose. The purpose of this lab is to set up an experiment in which we are able to determine the amount of excess charge on a piece of clear tape using fundamental physics principles. And here's a quick model of what we will be doing. The floating piece of tape is going to be tape B, and the other one is tape A. Some of the fundamental physics principles we'll be using are Coulomb's law, and then the charge of an electron. And then we also, of course, need Newton's second law, F equals ma, and this also tells us the gravitational force, which is F equals mg. Before we get started, here's a preview of our main results. And we found that there was an excess charge of 2.8 times 10 to the negative 8th coulombs, which corresponds to a deficiency of 1.75 times 10 to the 11th electrons. We also found that the magnitude of the electric force and the gravitational force acting on tape B are both equal to 0.000196 newtons. This is also shown in the computational model here. And here are some of our calculations from the lab. Let's get started with the analysis. Here are the steps of our experiment, and let's get started with the assumptions we'll be making. First, we'll be assuming that each tape represents its own point charge and that the experiment takes place in a vacuum with the absence of air resistance. We'll also be assuming that both pieces of tape are symmetrical, meaning they're the same length and have the same charge. We'll also assume that no charges will be lost or gained when handling the tapes during the lab. Here's the initial conditions, and we measured each tape to be 8 inches long, or about zero point 0.2 meters. And since we know the density of each tape, we can calculate the mass, which is 0.0002 kilograms of each piece of tape. The experiment involves pulling a piece of tape off another one, which generates static electricity. And since our piece of tape is positively charged by the principle of polarization, it is also attracted to electrically neutral objects such as our hand, and it's repelled by other positively charged objects. By creating two equally charged pieces of tape, this allows us to calculate the weight of the tapes using its density and then measure the separation distance at the point where tape A is able to make tape B float, as shown in this diagram. This is our setup, by the way. And this allows us to calculate the electric force that tape A exerts on tape B. Here are some of our calculations. Here we found the mass of the tape and then calculated the gravitational force on tape B and set this equal to the electric force. Since we know that the separation distance is 6 centimeters, we can use Coulomb's law to find the electric force. We know the electric force is equal to the gravitational force, so we can calculate the charge from each piece of tape, which came out to be 2.8 times 10 to the negative 8th coulombs. Here's the coding portion. Real quickly, here's Coulomb's law, most importantly, and then the initial conditions are up here, and then more calculations for our plot, which we'll see right here. The electric force magnitude is 1.96 times e to the negative 3 newtons, which we found earlier, and here's a quick model from our computations. And here are some potential errors. First off, air resistance. There's wind in the lab room that could have affected the separation distance, among other things. Charges would definitely have been lost when we were handling the tapes. And then also, the charges are probably not distributed equally throughout the entire surface of the tape. And then obviously the two tapes, I mean, there's human errors, so they're gonna have slightly different charges and slightly different lengths. That's just unavoidable. Here, what if the electrons had positive charges? And if the electrons had a positive charge, then this means that the net charge on each piece of tape would then be negative 2.8 times 10 to the negative 8 coulombs instead of positive. But since there's still polarization, these negatively charged tapes will still be attracted to neutral objects such as our hand or the table. But otherwise, the rest of our calculations would mostly stay the same, just with different signs where the positive becomes negative. Why is it important to handle the charged tapes as little as possible? And that's because when we handle the tapes, the charges can be lost or gained electrons will be transported from one material to another. So it's important to handle them as little as possible. And also handling the tapes can affect the distribution of the charges on the tape, making certain areas on the tape have weaker charges than others. All of this can lead to slightly different results in our calculations. Thank you for your time, and thank you to SlidesGo for this nice presentation. And please give me a 100. Thank you.